Our next lesson is 5.7. Apply the fundamental theorem of algebra. The fundamental theorem of algebra says this: if f of x is a polynomial of degree n and n is greater than 0, then the polynomial has up to n real solutions and exactly n complex solutions. This means we can now have complex zeros as solutions. Anything that's a complex number, remember, was written in the form a plus bi. Determine the number of solutions for the cubic function and then find them. To determine the number of solutions, we look at the degree of the polynomial. And in this cubic function, the degree is 3. What this means is there are up to 3 real solutions. And I'm going to abbreviate solutions right there. And there are exactly 3 complex solutions. Now, the unique thing about complex solutions is they include, and I don't know why I didn't abbreviate that one. Oh well, it is what it is. They include both real and imaginary. Now, to solve, let's go ahead and keep it equal to 0 like the original form. X cubed plus 5x squared plus 4x plus 20. Remember, we have a lot of options for solving. Factoring would be an actual choice for us here if we group x cubed and 5x squared and then group 4x plus 20. In that first parenthesis, we could factor out x squared, and we would have x plus 5 left over. In that second parenthesis, we could take out a 4, and again we have x plus 5 left over. Now, something we have to keep in mind, whenever we have that parenthesis, remember it's only written one time as a factor. The parts on the outside, the x squared plus 4, creates the other factor. X squared plus 4 isn't factorable. Therefore, when we solve and set each of these equal to 0, if I start with that first parenthesis, setting x plus 5 equal to 0, we'll just subtract 5 to move it over. Simple enough. X equals negative 5. But when I set the other one equal to 0, watch this, x squared plus 4. Because it doesn't factor, we're just going to move that 4 over, and we have x squared is equal to negative 4. That's a 4. Let's make sure to fix that so that looks better. Okay, try that again. And when we square root each side, the other day when we did lesson, I believe it was 5.5, we stopped because it said in the directions, that was my cat sneezing, sorry about that. It said in the directions to just find real solutions, but now we're finding all the solutions. What this means is we're going to include plus or minus, we're going to include I, and then the inside becomes 4. And if you remember, that means x is going to equal plus or minus 2i, because the square root of 4 is 2. Now we have exactly 3 complex solutions, 1 real solution with 2 imaginary solutions. Let's try another one. Determine the number of solutions for 2x to the 4th minus 10x squared minus 28 equals 0. For this polynomial, the degree is 4. Again, this means we have up to 4 real solutions, and it's possible to have 4 actual solutions that we could graph on a coordinate system. But it does have exactly 4 complex solutions, which include both real and imaginary. So I'll abbreviate solutions that time. Nope, that's complex. Oh, so is that word? Wow. All right, let's fix that. Sorry, everybody. There we go. We're just going to go with that. All right, so we have 2x to the 4th minus 10x squared minus 28. It's already equal to 0, so that first part's done for us. Recognizing this is a quartic function, also I can see that there's a common factor. If we take the 2 out of each term, that would leave us with x to the 4th minus 5x squared minus 14. Now, if we think about splitting up this quartic function, remember x to the 4th is a perfect square. We can split that apart into x squared and x squared. Now think, What are two numbers that we could multiply to get 14, but add to get that -5 in the middle? If you thought -7 and +2, that would work. Recognizing, though, that there's that 2 out in front. We've had this situation a couple of times. If you just have a coefficient out in front without a variable, we can actually divide both sides to eliminate that coefficient. It doesn't impact our zeros. And then what that would allow us to do is take each parenthesis and set it equal to 0 separately. Now if I move 7 over, because it wasn't factorable, we would get x squared is equal to +7. Take the square root of each side and x will equal, remember that plus or minus to indicate two of the solutions, and then the square root of 7 is simplified. Now when we do this with x squared plus 2, moving that 2 over is going to make it negative. And when we take the square root of a negative number, just like up above, we're going to have plus or minus, we're going to have I, and the square root of 2 in this solution set doesn't simplify either. We have 4 total solutions, 2 that are real and 2 that are imaginary, all falling under that complex category. Changing gears, the sum and product rule. It says given 2 zeros of a function, you can create a quadratic expression. This is going to indicate that we're working backwards. So now I'm going to give you the solutions for the polynomial and we're going to create it, starting with a quadratic expression. If you're given 2 zeros, you can create a quadratic expression or factor using the following template. X squared minus, take the sum of your zeros, and that's the coefficient for x, plus the product of your coefficients, that's your constant. Ooh, and that's not going to fit. What a surprise. All right, there we go. We'll get that to fit right there. Make sure to have this template written down. X squared minus the sum of x times the product. Your plan is to look at the given zeros of the function and literally determine what the sum and the product are. Let's see how this works with an example. Write a quadratic expression with the given zeros, 4 and 5. Technically what this means is that our graph would cross the x-axis at 4 and at 5. Remember, those numbers are the zeros, they're the x-intercepts, they're the roots for our function. If we're applying the sum and product rule, we're literally finding the sum and the product. The sum when we add the 2 roots together is 9. That's going to be part of our quadratic expression. The product for times 5 is 20. That's all you need. You need the sum and the product of your 2 zeros or roots. Now that template that we wrote up above, x squared minus the sum times x plus the product. The sum and the product are really just numbers in our quadratic expression. Also notice for this quadratic expression that your lead coefficient is always going to be 1. So we know that the sum is 9. We're going to plug that in right in front of x. That becomes x squared minus 9x. And then the template goes plus the product. Our product is 20, so plus 20. The quadratic expression x squared minus 9x plus 20 has zeros of +4 and +5. What happens when one number is negative and one number is positive? We still apply the same idea. This means that one of our zeros is -6 and the other is +2. To find the sum of these two zeros, -6 plus 2 is -4. The product, when we multiply, is -12. Done. There's the sum, there's the product. Our template, again, x squared plus, not yet anyway, x squared minus the sum times x plus the product. Write this out as many times as you need until you have it memorized. Now the sum is -4. So when we substitute that in, and I was going to write the word substitute as I wrote that. Let's try that again. X squared minus the sum times x plus the product. Notice we have a double negative here. That's actually going to change it to a plus. X squared plus 4x, and then plus negative 12 becomes minus 12. There's your quadratic expression that has zeros of negative 6 and positive 2. For our last example in this section, I'd like you to change it up. Both of our solution sets for the first two problems were real solutions. What happens when you have those imaginary solutions? So instead of 7 and negative 7, please just change that to 7i and negative 7i. Two solutions, let's create the quadratic expression. Applying the sum and product rule, the sum of these two complex numbers, watch what happens here. If we take 7i plus negative 7i, they're opposite signs, and that makes them cancel out. Our sum is 0. The product, this is going to bring us back to chapter 4. If we multiply positive 7i times negative 7i, positive times negative 7 is negative 49, and I times I is I squared. Remembering from chapter 4 that I squared equals negative 1, that gives us negative 49 times negative 1, which actually gives us a product of positive 49. As we create that quadratic template here, x squared minus the sum times x plus the product. If we substitute in 0 and positive 49, that 0x term eliminates. So we have x squared plus 49. There's your quadratic expression with two imaginary roots. As if quadratic expressions weren't enough, we can create polynomials of higher degree with real solutions and complex or imaginary solutions. Write a polynomial with degree 3. That's going to be a cubic polynomial that has rational exponents and the given zeros, negative 1, 2, and 4. Again, this means x equals negative 1, x equals positive 2, and x equals 4. Now, if we know that that's what our solutions are, or our zeros for x, in factored form, if x equals negative 1, then the factor is x plus 1. It's the opposite sign. X equals 2, that means the factor would be minus 2. And x equals 4 would indicate that our factor is x minus 4. To write the polynomial, we need to multiply this all together. We don't want to leave it in factored form. So what I want you to do is actually FOIL the first two together. Pause the video and multiply them, combine like terms, then press play, and we'll figure out what to do with that x minus 4 at the end. If you did your multiplication and combined like terms, you should get x squared minus x minus 2. Drop down that x minus 4, and now we're going to FOIL everything. X squared times x and x squared times negative 4 would be x cubed minus 4x squared. Then take negative x times x and negative x times negative 4. That would give us negative x squared plus 4x. Then last but not least, negative 2 times x and negative 2 times negative 4 would give us minus 2x plus 8. Because we're writing a polynomial, what we have to remember is that that's an equation. So we need to start off our template as f of x equals. And then we'll just combine like terms, kind of like what we did up above. We have x to the third power minus 5x squared, and then plus 2x when we combine like terms. It's a plus right there. And then plus 8 as our constant at the end. So look at that, everybody. We created a cubic polynomial that would cross the x-axis at negative 1, 2, and 4. And that's going to end our lesson for today. We'll finish the rest of the problems, or the rest of the notes in class.